Good afternoon, sir. Myself, Deepak. I am a research scholar, Department of Electronics and Communication Engineering, SRAM Institute of Science and Technology, Delhi NCR campus, Ghaziabad. Here, today I am present our research work titled Analysis of FinFET-based SRAM cells with improved parameters. With improved parameters. First, we are discuss about the introduction about the SRAM cells. As we know, tomorrow demand is daily increase, the minimize circuits, and the SRAM memory cell is very important component to design any electronic circuit. The increase in the transistor densities within the VLSI has to lead a growth into the on-chip on-chip cell design sizes, resulting in the higher power consumption due to the thermal capacity. Here we use SRAM, design SRAM cell with FinFET technology because FinFET technology is having the minimized leakage current. This means the most common type of memory is SRAM cell, which occupy more than 60% of the chip area. All memories have occupied more than 80% of the circuit area, and that micro devices means maximum micro devices have the 80% area is covered by the memories. The development of SRAM cell using the FinFET technology for the implementation with the primary objective of mining criteria memory parameters, including parameters named as power dissipation and the noise voltage. Because power dissipation is main component for any electronic circuit. As circuit is reduced, then power dissipation is increased. In this article, multiple simulations are carried out among the conventional SRAM cell, means normal CMOS or MOSFET used for designing the SRAM cell, and the FinFET based SRAM cell for designing the 6 transistor, 7 transistor, and 8 transistor based SRAM cell with the help of Cadence Virtuoso tool with the 45 nanotechnology. FinFET devices provide a variable method to create highly integrated power efficient circuit for the low power digital applications due to combination of enhanced flexibility and decreased short channel effects of the FinFET. Why we use FinFET? Here we use a FinFET due to the some advantage over the MOSFET. First one, the large number of transistors can be incorporated into a single chip. FinFET technology is suitable for the IC fabrication as its high stable scalability for the given footprint area compared to the normal MOSFET or CMOS. As the chips are downsized, reduce the size and number of transistors are increased, this compactness brings the drain and the source closer and reduce the gate control over the channel carriers. Means when we compress when we compress size between the drain and source, then reduce the gate control over the channel. This type of short channel effects can cause seriously issues in the MOSFET. The presence of fins gives FinFETs better short channel behavior as compared to normal MOSFET. To improve the short channel behavior, channel doping is common in planar MOSFET. The wrap around the gate over the thin body makes channel doping optional in the FinFET, which is not present in normal MOSFET. Therefore, no dopant, no dopant is induced fluctuations are present in the MOSFET. Whereas in the case of simple MOSFET, various fluctuations are present. Similarly, the leakage current and the leakage voltage are responsible for the leakage power in switching devices. Since MOSFETs are devices with low leakage current, with their power consumption is less than compared to any other FET like MOSFET or CMOS. In the planar MOSFET, the device drive strength is dependent on the channel width, whereas in the FinFET transistor, the drive strength can be increased by incorporating multiple or longer fingers. Means We can easily increase the drive strength. We can easily increase the drive strength in the FinFET by increasing the size of fins. As a higher drive, current can be reflected as fast switching times in FinFETs. Otherwise, it can be said that the three-dimensional FinFETs are high-speed devices compared to the MOSFET devices. It is easily fabricate multiple gate devices using the FinFET technology, where with the help of MOSFET, which is very, I am, it is very tough to fabricate multi-gate devices. And at the last and main point is the FinFET offer an excellent sub-threshold slope and higher voltage gain as compared to the planar MOSFET. And now the reason what is the FinFET? Actually, what is the FinFET? FinFET is a three-dimensional field effect transistor as shown in figure. This one, this side is one side has a source, another side has a drain. But this is the main difference between the MOSFET and the FinFET. MOSFET having a gate between the source and drain on a single side, side as figure shown, but FinFET have a gate between the drain and source on the both side, right side and left side, both side. Is a multi-gate, which means more than one gate having the FinFET. FinFET is a multi-gate FET. A FinFET has a two gates. It is named as a three-dimensional structure above the substrate, looks as a fins. Hence, this MOSFET is known, this FET is known as FinFET. It is a three-dimensional transistor and widely used in integration circuits, recently in place of the normal CMOS and MOSFET. The gate is webly. The gate is fully wrapped around the channel on three sides. This is as figure shown. This is two side left and right. This is left, this right, and the upper side. Means all three sides are covered by the gate between the drain and source, which is easily controlled the reduce leakage current. With this channel is gate is used to reduce the leakage current as compared to the planar FinFET. The FinFET devices have significantly faster switching times and higher current density as compared to the planar MOSFET or CMOS technology. In this designing, we use some method. In our research, we use a design of 6 SRAM cells. 6 SRAM cells based on the transistor 6 transistor, 7 transistor, and 8 transistor with the help of Cadence Virtuoso tool at 45 nanometer technology for measuring the average leakage power and average noise power. These three types of transistor SRAM cells we design first of all normal planar technology means CMOS technology or MOSFET technology, and then same transistor SRAM will design with the help of FinFET technology and calculate and compare all the parameters for the average leakage power and the average noise power at different power voltage input power supply. Now here what is the leakage power? Leakage power is a reflection of a total power increase as low frequency drops during the power supply in unused parts can be saved. Unused part means that part of the circuit which are not used during the process. For a gate, it is a small fraction of the total power and it can be significant for every large circuit. Scaling down feature requires the lowering the threshold voltage, which increase the leakage power roughly double with each shrinking. Means when we scale down the threshold voltage, normally circuit produce leakage power increase as double. Here the multiple threshold devices are also used to reduce the leakage power. This is the design flow graph which are used to design our SRAM cell. Here we start the first Cadence Virtuoso tool. After this, first we design a statement diagram for the SRAM cell using the CMOS, planar MOSFET and Same FinFET. Then we check the systematic diagram. If error is reduced, increase, error is comes, then we process first step repeat, and no error is come, then we save the systematic diagram and create a symbols for the SRAM cell. Same process, I have typed two types, and then no error is in my circuit, then we convert into the separate simulation file and verify the analysis report. After the satisfaction of simulation, we find the different values of different values of power dissipation and voltage, noise voltage at different input voltage supply at the input. This at the input. This is the first which are designed six transistor SRAM cell with the help of conventional MOSFET, normal MOSFET, not the FinFET. This is the bidirectional in the work as a three sub. This SRAM cell work in the three modes: first, hold, active, and standby. In the standby mode, the word line transition from the high to low means when WL is 0. This WL line is 0. The bit line, whenever 0 or 1, the bit line, this one BL, is 0 or 1, retain the data within the inverters. This is one inverter P1 and P2. P1 and N1 makes the one inverter, and P2 and N2 makes the another inverter. These two inverters are joined back to back. The output of first inverter is connected as the input of second inverter, and the output of the second inverter is connected as the input of first inverter. These two N3 and N4 is the two NMOS transistors. These two inverter work as a cross-coupled amplifier. This is cross-coupled. During the right operation, when the WL, this one first is the WL 0, and then now when word line WL is 1, then enable the introduction of new data bit line BL, and this data is then written onto the Q and Q bar. Q is the normal output, and QB is the output with bar, means complemented output of the transistor cross-coupled transistors P1, N1, P2, N2. Similarly, the second design is 7 transistors. In this, main difference in the 7 transistor and 6 transistor is this N1. This is N5 transistor. This is a NMOS transistor is connected between the two inverters, which is connected as a cross couple. E1, P1, E1, N1 is the inverter 1, and P1 and N2 is the inverter 2. Here a NMOS transistor N5 is connected between these two inverters for storing the data and refresh the word line. Similarly, the two transistor and one transistor operated with the word line on their dates. In this SRAM, an N5 is used to control the MOSFET, acting as a bridge between the two latches or two inverters. During the read operation, the N5 transistor is working, and the value of SRAM cell output is sensed by a sense amplifier. The bit lines BL and BLB, bit line or bit line with bar, can be either pre-charged or discharged during this phase. The standby mode operates similarly like cis transistor SRAM cell. This is the third our design, 8 transistor SRAM cell using conventional MOSFETs. In this design, we use same two inverters P2 P1, P2 N1, P2 N2, and P1 N1 are connected cross-coupled, and two NMOS transistor N3 and 4 at the output of inverters. In this, two transistor combination N5 and N6, both are the NMOS transistors are used at right side of this SRAM cell. These are the SRAM cell. N3 and N4 transistor work as a normal pass transistor. In this SRAM cell, two modes read and write. They in the write mode, the operation is similar to the SRAM cell, which have discussed already switch transistor SRAM cell. Transistor when word line is high, the transistor from low to high results in the storage of BLB and BL. BLB and BL data is stored in Q and QB outputs. In the read mode, the storage data at QB is accessed by the activating the read line, read B line, this one, RBL, read bit line when high. This operation is facilitate N5 and N7, N5, N7 transistor using the ground node and sensed by a sense amplifier. Sense amplifier. This is the another same I have discussed 6 transistor, 7 transistor and 8 transistor SRAM cell using the conventional FETs. Now we discuss 6 transistor, 7 transistor and 8 transistor SRAM cells using the FinFET. As figure shows, this figure 5 shows the FinFET based SRAM cell using 6 transistor and this shows figure 6 as FinFET based SRAM cell using the 7 transistor. Here we see figure 5 is similarly like the 6 transistor using the conventional. Main difference is there where we use normal PMOS and NMOS. Here we use P1, N1, P2, N2, N3, N5. All these transistors using the FinFET technology. Similarly, here this is the N5, P1, P2, N1, N2, and N3, N4. All the 7 transistors are designed with the FinFET technology. This is similar 8 transistor FinFET based SRAM cell. The structure is same as conventional SRAM cell, but these main difference is there where we use the MOSFET, here we use the FinFETs for designing the SRAMs. With the help of FinFET, we can easily reduce the leakage current and reduce the power dissipation of the cell. These are some results which we are found during the simulations. This is the table. One shows the comparison of average power between the conventional SRAM cell and FinFET based SRAM cell at different power supply which is applied as an input 0.1 volt, 0.2 volt, 0.3 volt, 5 up to 7 volt. Here we easily compare which is the best FinFET or conventional SRAM cell. Here we point at means we take the 0.5 volt as an input, then SRAM cell 6 transistor gives the power dissipation in nanovolts 11.33 and there same potential applied, same power supply applied using the FinFET 8.96 only. Similarly, 7 transistor designing 0.620 and FinFET used 70. Similarly, the table is shown easily be analyzed. Then FinFET transistor based SRAM cell reduced approx 20% power dissipation as compared to the conventional SRAM cell. Secondly, second table is given the comparison of average noise voltage. Comparison of average noise voltage between the conventional SRAM cell and FinFET based SRAM cell at similarly different power supply voltages from 0.2 volt to 0.7 volt for all the 3 designing 6 transistors, 7 transistor and S transistor, 8 transistors SRAM cells. This is a comparative result study as compared to the earlier literature reviews which different researchers work on the different transistor SRAM cells. Like this, these 3 already designed 6 SRAM transistor cells that give the power dissipations. This one, 7 this one, and 8 this one. Here these last 3 designs we proposed for the 6 transistor SRAM, 7 transistor, 8 transistor with the average noise voltage and comparatively average power dissipation. This is the comparative chart comparative study chart for the SRAM cell for the power dissipation. This power dissipation is the y-axis at microvolt, and this is the bar chart for the different earlier researchers designed the SRAM cell. First of all, Dewey et al. Cis transistor design, Muscat et al. Cis transistor design, MB Rao et al. Cis transistor design gives the power dissipation like approx 50, approx 40, and approx 30 microvolt. And we proposed which is the sixth transistor FinFET SRAM cell produces 25 approx microvolt. Similarly, these two seven transistors were earlier the researcher Lakshmi TV and the Premlata, and our proposed provide the approx 18 microwatt average power. Similarly, these are the four earlier researchers which have worked on the 8 transistor SRAM cell, and our proposed 8 transistor FinFET based SRAM cell gives the minimized approx 26-25 microvolt power dissipation. As the conclusion, FinFET based design SRAM cell as compared to the conventional SRAM cell gives much better results for the power dissipation. These are some FinFET based SRAM cells applications. First of all, high performance computing. Second one is mobile devices. Third one is the consumer electronics. And fourth one is the network equipment. First equipment used in the processor and high speed cases where the performance is critical analysis. Network equipment means the utilized in routers and switches where the high speed data access and the low latency are required. These are the some points as the conclusions of our research. First of all, the analysis reveals that the FinFET-based cis transistor SRAM cell outperforms its conventional counterpart primarily due to its smaller size. Second one is the due to the better device features of the FinFET-based SRAM cell in the low voltage operation. This has become the most promising technique for lower the VDD, means the power supply will be applied for the circuit operation in the FinFET technologies. And third is the main our conclusion in the shape of result. The result shows that the proposed FinFET based SRAM cell has a 17% reduction in the leakage power as well as the 35% reduction in the noise voltage. When we compare the same design structure like 6 transistor, 7 transistor, 8 transistor, same is comparison. 6 transistor conventional with the 6 transistor of FinFET SRAM cells. These are the some references which are used in our research. Thank you.